Hello, everyone. Today we are going to be discussing a quantum mechanical model to showcase the vibrations of molecules. My name is Becker, and let's get started. So first, we will begin with a classical model. Consider two masses connected by a spring. If you pull one mass, an opposing force given by F equals negative kx, k being the force constant written in units of newtons per meter, will be created to resist the motion of this stretch or this pull. So if we pull our mass outward, the force is going to be opposing that and pulling the mass inward. And if we push this inward, well, our force is going to be pulling outward. So yeah, when we release our mass, it will then oscillate back and forth until eventually it settles back into its equilibrium. Now, for any two objects, there will be a center of mass that does not move. If we have a really big mass connected by a spring to a very small mass, this center of mass is going to be very close to the big one, something like that. But whether our system has a large and small mass, two masses of equal sizes, there will always be a center of mass that does not move when our spring oscillates. Now, we can simplify this two-mass system to a one-mass system called the reduced mass, which will oscillate on a spring attached to an immovable wall. We kind of see that right here. Now, to convert from our two-mass to one-mass system, we can use the reduced mass is going to equal our mass 1 times our mass 2 over mass 1 plus mass 2. And then this will be, this over here, our reduced mass, just like that. Now, the total energy of our system when it is oscillating is going to be the sum of the potential energy plus the kinetic energy, which can be like this, kinetic energy plus potential energy. Now, we can use our force constant and some other variables to write this a little bit more detailed. So our total energy is just going to be 1/2 times the reduced mass times velocity squared. This is just our kinetic energy, 1/2 mv squared, plus 1/2 kx squared. This comes from our spring constant and describes the potential energy stored in the spring when we oscillate it one way or the other. And this is going to be helpful characterizing our system, and it can be applied to our quantum system. Now consider a simple molecule such as HCl with two atoms. We can imagine this much like our classical system where we have, one big mass and a small mass connected by a spring. When these vibrates, they're going to be going back and forth just like this. And much like we did with our classical system, we can convert this to our reduced mass system. Now with any quantum system, we can write our Schrödinger equation, which is just going to be our kinetic energy operator times the wave function as a function of x plus our potential energy operator times the wave function is going to equal the energy times our wave function, just like this. And if we just want to flesh this out a bit more using that total energy equation we wrote last slide, we will get negative h bar squared over 2 times the reduced mass times the second derivative of the wave function with respect to x plus 1/2 kx squared times a wave function equals the total energy times the wave function. And if you look back at your notes for some of the previous Schrödinger equations we wrote, such as for the particle box, we can actually see it's pretty similar. We just have this potential energy term, and we replaced our mass with the reduced mass because of our system we have up here. And as we did with particle in a box, we can solve our Schrödinger equation. Unfortunately, this solution is not as straightforward, but when we solve it, we are going to obtain this solution. The nth wave function as a function of x is going to equal our normalization constant times our Hermite polynomial times a Gaussian function for n equals 0, 1, 2, and so on, integers. This alpha term is just going to be this right here. square root of k times the reduced mass over h bar squared. Now, our Gaussian function is just going to be like your standard bell curve. We have a function just sort of like this. Now, our Hermit polynomials are going to be a well-known set of functions that we will not derive today. Anyways, if we look at the solutions to the first couple ends of our system, we see these right here. We have our wave functions for values of n equals 0 to n equals 3 shown on this slide. And it's a lot of information, but kind of breaking it down, we have our normalization constants, our Hermit polynomial, and our Gaussian function. Now, taking these wave functions, we can plot them as energy versus position, and we get this sort of graph right here. This yellow region is going to represent the classically forbidden region, where E is going to equal V. And if you remember, V equals 1/2 kx squared, so it makes sense that this is a quadratic function right here. But anyways, we can see some key similarities to the particle in a box. For our 0th wave function, we just see 0 nodes in it, which is expected for the ground state of our system. As we go to our first excited state, we see 1 node in our system, and so on and so on. Basically, we have n minus 1 nodes for each energy level, which is exactly what we expect for a particle in a box. Anyways, we can write the energy of our system. To do that, the energy of the nth level is going to equal h bar times the square root of k over the reduced mass times n plus 1/2. We can also rewrite this using some substitutions as h times the frequency times n plus 1/2. And this is going to be very useful later on when we are dealing with vibrational spectroscopy. But anyways, that is going to wrap up our discussion of how we model the vibration of molecules. The classical harmonic oscillator is a powerful way to think of our system. We will find that it has limitations, but it serves as a nice foundation to describe just exactly how molecules vibrates. Anyways, thank you all so much for watching, and have a great day!